So welcome to the second part of the magnetic properties of the materials course. This is the first of 4 lectures looking at the phenomenon of superconductivity. And in this part of the lecture, I'm going to talk about some of the evidence for superconductivity. So in 1908, Onnes was the first person to manufacture liquid helium. So he was working in Leiden in the Netherlands, and so helium becomes liquid at 4.2 Kelvin. And he was able to liquefy helium, and then by reducing the pressure could also lower the temperature. So he was able to go about as low as 1.5 Kelvin. Okay, and this was the first time in the world that those sorts of temperatures had been possible. And this basically led to a whole new era of low temperature physics. So people were able to explore properties of these really low temperatures. Now, it had long been controversial as to what, for example, say the conductivity of metal would happen to the conductivity of metals as you approach absolute zero. So some people thought that as you approach absolute zero, everything stopped. So the electrons wouldn't be able to travel through the metal. To me, that seems a little bit weird, but that is what some serious scientists thought. Others just sort of extrapolated back from what we knew already at low temperatures, that as we decrease the temperature, we expect the amount of scattering from phonons to decrease, and so the resistivity will decrease. In principle, if we could get a perfectly pure metal, it should decrease to zero as we got to absolute zero. Now, in 1911, Onnes tried to do this experiment. He thought, well, let's see what happens. And he looked at the conductivity of mercury at low temperatures. And the result was completely unexpected, because as he lowered the temperature to a critical, particularly a critical temperature, the resistivity dramatically dropped. Okay, so Tc for mercury is about 4.2 Kelvin. Okay, and as you got to 4.2 Kelvin, the resistivity was so low he couldn't measure it. Okay, he didn't have the apparatus to measure it. So to all intents and purposes, it had dropped to zero. Okay, and that's what we saw in this behavior here. Okay. So what are we going to look at in these 4 lectures? Well, we're going to begin by reviewing the experimental evidence. Okay, what are the properties that we can measure about superconductors that is unique from the materials we might study, what we would call normal materials? Having looked at all the evidence, we'll then review it. What can we learn from this evidence? What can we deduce about what must be going on? Having done that, I'll get to the answer, or at least part of the answer, and the answer is known as BCS theory. Okay, you might not like the answer, but we will explain what this tells us about the superconducting state, and then we'll see how this slightly initially it seems really quite strange and quite weird idea actually accounts for all of the properties that we know, at least about elemental metals when they superconduct. Okay, so we'll see how BCS theory and some of the simpler theories that derive from it can be used to look at properties of the superconducting state. And then finally, we'll do a bit of an outlook, and we'll see how this field has gone on and expanded. We'll look at phenomena such as high temperature superconductors. So I did a little bit of a count before, and I just wanted to convey the sort of intellectual effort that there's been in the 20th century in trying to understand superconductivity and the puzzles it's presented and the new interest in physics and materials chemistry that has developed from it. I did a quick count, and I found 18 individuals who've been awarded a Nobel Prize for work relating to superconductivity. Okay, that's really quite a large fraction of the Nobel Prizes. Okay, But what would I say is superconductivity still has some huge puzzles in it, and I'll get to some of those by the end of the course. Things that are simply not well understood, and absolutely for sure there will be further Nobel Prizes awarded for work in superconductivity. Okay, so on to looking at some of the evidence. Okay, let's go back to looking at the resistivity. Okay, so what we know is that when we cool the material below a critical temperature, a current can pass without resistance. What that can mean is there can be a persistent current. So if I was to make a sort of donut-shaped thing, some sort of toroid, I could induce a current in this, and I could look to see how long it lasted. In a real material, you'd expect the current to decay quite quickly, okay, because of the losses due to resistance, collisions with phonons, collisions with defects. Okay. If you do this in a superconducting material, you can look and see how much the current decreases over a year or over the period of 2 years. Okay. And typically what you would find is you can't measure a decrease in the current. This means, on the basis of experimental, the limit to how accurately you can actually measure a current, it means the decay time is at least the order of 10 to the 5 years. Okay, that's really quite a long time. So the resistance, if it isn't exactly zero, is extremely close to zero. Okay, so it means within experimental error, we think the resistance is less than, say, 10 to the 25 ohms per ohm meters. Okay. Just for comparison, copper is considered to be a good metal, and the resistance of copper is about 10 to the 8 ohm meters. So we've got many orders of magnitude difference. Okay. Now, just to recap what we know from a normal metal. So in a normal metal, we expect two contributions to the resistivity. We expect there to be a defect contribution, and we expect there to be a phonon contribution. Now, the effect of phonons increases with temperature, increases as the fifth power of temperature, so pretty rapidly. And that kind of makes sense. We've got higher temperatures, the lattice is vibrating more, and that gives electrons more to scatter off, so it increases the resistivity. Defects also cause scattering. Now, here I've sketched on what we'd expect on the basis of this sort of graph for the resistivity of a material. Okay. Now, if I was to make a sample that, for example, had fewer defects, I could well get a curve that did something like this. Okay, or going a bit lower. Okay. And in principle, of course, if I could make a material with no defects, its resistivity would go to zero, but only at absolute zero. Now, in practice, I can't make a material with no defects in. Entropy kind of stops me from doing that. So there's always going to be some defects in there. But this is the behavior that we see in superconductors is completely different from that. So something is going on at this transition temperature. Now, very soon afterwards, so owners did this in mercury. He quickly tried it out in a few other materials. He tried it out in tin and lead and found exactly the same phenomena. It was also quite rapidly found that if you apply a magnetic field to the sample, you can destroy the superconducting state. So what we would say is you can make the material a normal metal again just by applying a magnetic field. And again, purely experimentally, it's been found that there's a critical field here, I'm given that BC, which depends on the temperature. Okay. And in fact, mathematically, it's found that they roughly obey this relationship here. Okay. So what that means is that as so this is temperature on this axis and magnetic field applied on this axis. Okay, and if we were, say, very close to zero, we would have a critical field BC. But as I go to a higher temperature, my critical field becomes lower, so it becomes easier to destroy the superconducting state. So very close to CC, only a very small magnetic field can be withstood before the material is driven to be normal. Okay, so if you think about this as a little bit like a phase diagram, you could think about this region here as this is the superconducting region, and outside here is the normal. Okay, so that was found experimentally fairly early on, that the magnetic field can destroy the superconducting state. Now, armed with the liquid helium and the ability to do this, people very rapidly looked for superconductivity amongst other materials, in particular looking amongst elemental metals. And it was found to be a pretty ubiquitous property. Okay, a great many elemental metals are found to exhibit superconductivity. So we've got things like aluminium. So what I'm giving here is the transition temperature and also the critical field. And that would define a series of these sorts of curves. So these would be curves for different elements. Okay. What can we note? Well, there's a whole range of materials. So aluminium, which we know to be a very well modeled by free electron gas that can superconduct, but it's a very light metal, so it's quite high up in the periodic table. Something like lead, okay, way down in the periodic table, that also has a superconduct, slightly higher transition temperature and a higher critical field. Transition metals, so zirconia, molybdenum, both transition metals, both superconduct, although their TC is really quite low. And it isn't the case that a high TC is correlated with a high critical field. Okay, so let's the first three do correlate, but then we have something like vanadium, which has a lower TC than lead, but a much higher critical field. Okay, so this is the key thing, that whatever's going on here must be pretty ubiquitous. Okay. Now, I think there's something that stands out in this table. That if you think about the critical fields here in Tesla, they're all pretty small. Okay, I mean, if you think about a pretty strong magnet you could get in the lab, might be the order of 1 Tesla. Okay, an MRI machine, 5 Tesla. A big NMR magnet like the one that's actually in the basement of the building where I'm recording this lecture would be the order of 20 Tesla. So, that gives you sort of a sense of how big magnetic fields are possible. Most of these magnetic fields are actually really quite small, so we're talking 1/100th of a Tesla. Vanadium, however, has a 1 Tesla critical field. That's starting to get to be sort of useful. Okay, so that's interesting. So vanadium seems to be a little bit different from the other elements. Now, for the moment, I just park that thought, and we will come back to it in the final lecture as to why is vanadium different from the other materials. But at the moment, it's a little bit of an outlier. Now, the other thing that was found by some really very careful measurements is that the transition temperature depends on the isotope of the element. So it's possible, for example, to isotopically enrich a sample of a metal. So we can have a sample of mercury, for example, that's containing one particular isotope and another one that contains a different isotope, and then we could mix between the two so we can control the weight of the atoms involved. And that does make a difference. So the slightly lighter mercury has a slightly higher transition temperature. Okay, not by very much, 4.185 versus 4.146, so 4/100th of a Kelvin. Need a pretty good thermometer for that, but it's an effect, okay, and it's been noted in other materials. So that's an interesting piece of experimental evidence that the transition temperature is somehow linked to the mass of the elements involved, not just the bonding. So the other piece of experimental evidence actually came quite a while later. And so doing some experiments in 1933, Meissner and Ochsenfeld found that a superconductor expels a magnetic field. So if we start here with our sample of our material, so we've applied a B field, but we're above the critical temperature. So the lines of flux just will pass through into and through the material. Okay. Now we cool our sample down, and what it is found that when we go below the critical temperature, the sample somehow arranges itself to expel those field lines so that B is 0 inside the center. Okay, so B, the field inside here is 0, even though the external field is not 0. Okay, and so we often refer to superconductors as perfect diamagnets. So if you go back to your definition of susceptibility, this would be a susceptibility of -1. Okay, so it means that there is no magnetic field outside the material, irrespective of the B field we apply to the material. That's actually probably one of the more sort of commonly known properties of superconductors, because of course it leads to the idea of things like maglev trains. Pieces of superconductor will float above a magnet because they're trying to get out of the magnetic field to lower their energy. Okay, and I showed you a photo of paralytic graphite. Remember, the susceptibility of that was the order of 10 to the -5. Okay, -1 times 10 to the -5. So the effect here is significantly stronger. Okay. So what other evidence do we have? There's evidence from the heat capacity. So in the blue line here, I'm showing how the heat capacity varies with temperature for a normal material. Okay, it should just go linearly down to 0. What actually happens in the superconducting state is when we reach Tc, the heat capacity jumps up. Okay, it's discontinuous, it jumps up, but it rapidly drops down very close to 0. Okay, looking at it the other way, this actually looks like a sort of exponential function, and then a transition back down to the normal. Okay, so for the heat capacity, the superconducting state is acting very differently to the normal state. Now you might wonder, why have I drawn this blue line down here? Okay, because surely we're below Tc, the normal state has gone away. Well, actually what you would do is you'd apply a small magnetic field, because if you take one of those elemental metals we showed earlier, the critical field is quite small. So what we can actually do is we can keep the material normal all the way down to as low as we wish to measure, just by applying a small magnetic field. Okay, and by doing that, we can look at what happens to the heat capacity in the normal state. I mean, essentially, it's exactly what you get if you'd extrapolate the normal state at higher temperatures back down to lower temperatures. Okay, but you can actually measure both at the same time using this idea. Okay, and then finally, some really quite difficult experiments to do, which is to look at optical absorption. Now you'll look more at how normal metals interact with light in the electrical and optical properties course. But just to state what happens, so at optical frequencies, so light, both the superconducting and the normal states behave the same. So there's no difference. Essentially you expect the metal to be shiny, and both the superconducting and the normal states will behave in exactly the same way. But when you go down to microwave frequencies, the superconducting state behaves very differently. So at microwaves, you'd still expect metals to be reflective. But below a certain critical frequency, the superconducting state becomes transparent to microwaves. That does not happen in the normal state. And that, as we'll see later, when we unpick that, we'll discover that that was one of the key final pieces that gave rise to the final BCS theory of superconductivity. Okay, just to review the evidence, zero resistivity below a critical temperature. Okay, but that superconducting state vanishes above a critical magnetic field. It's also the case that there's a critical current density. So if you're in a superconducting state, there's a limit to how much current you can carry before you destroy the superconducting state and you go back to normal. That's perhaps not too surprising given the relationship between, of course, if there's a current, that also creates a magnetic field. So those things are kind of linked together. A pretty telling piece of evidence is the isotope effect, the fact that the mass of the atoms seems to affect the transition temperature. We've got the Meissner effect, where the material expels the magnetic field when it's cooled below the critical temperature. We've got a jump in the heat capacity at the transition temperature. And something I haven't dwelt on, but if you also look at the thermal conductivity, that's much lower in the superconducting state than you'd expect from the normal state. And then finally, there are the experiments on optical absorption and this somewhat anomalous effect when we look at the microwaves region. Okay, so in the next two sections, probably the second part of the first lecture, and the first part of the second lecture, we will unpick these and try to see what science we can extract out of all these phenomena.